Hi, so welcome to the video lecture on analysis of variance, which is the hypothesis test for comparing more than two means. So this test is called analysis of variance, which we abbreviate Anova. And let me start by giving you an example where we might want to use this. So we've got, in this example, 15 people who have high cholesterol, and we're going to randomly assign them to one of three groups. The first group is going to make dietary changes only. The second group is going to take a drug only, and the third is going to do both. Anova can determine whether there's a difference in the cholesterol levels of the groups after, say, a year of these treatments. The hypotheses will be, for this one we've got three groups, so we've got the null hypothesis is that all three of those groups are the same. If we had more than three groups, we'd have, if we had 5 groups, we'd have mu1 equals mu2 equals mu3 equals mu4 equals mu5. And the alternative hypothesis is always going to be that at least one of the means is different from the others. I want to point out here that that's different from saying that they're all different from each other. It could very well be that 2 of them are the same and one of them is different. So we don't say that they're all different from each other, but that at least one of them is different. Another thing I want to point out here is that unlike the other tests, this one doesn't have a one-tailed versus a two-tailed option. This is just, there's just the one possibility. The question comes up, why is it called analysis of variance when what we're trying to compare is the means? So I made these 2 graphs to show you, to kind of demonstrate. To determine if there's a difference in the means, we actually look at the variability. We look at 2 different kinds of variability. If we look at this first one has large variability within each group. Each group is very spread out within it. But the groups are not very far apart, so within the groups, there's a lot of variability, but between the groups, there's not a lot of variability. That's not going to be very good evidence that the group means are different from each other, because it looks like they overlap a lot. In the second group, the second graph, we've got 4 groups where there's a big difference between the means. In other words, a large between-group variability. Whereas within each group, they're pretty tightly clustered, meaning that there's small within-group variability. Okay, so the 2 kinds of variability we're looking at here are within-group variability and between-group variability. And in this case, we've got convincing evidence that the groups are different. So what we want to see to have evidence that the groups are different is we want to see small variability within the groups and large variability between the groups. So that's why we call it Anova. To do the calculations, we'll just do the calculations in StatCrunch and in SPSS. So we'll start with this example where we've got people with high cholesterol after 3 months. So I've taken this data and I've put it into StatCrunch, and we're going to run an Anova to see if there's a difference in the mean cholesterol of the 3 groups. So the first 3 columns here are our example. So we're going to go to Stat, Anova, One Way. And you just highlight all 3 of your columns. So highlight the first one and then press Shift and then highlight the last one, and it'll select all of them. And then just hit Compute. Okay, when we do that, we get a bunch of results, which I've pasted over here. So you do need to state what your hypotheses are. This time StatCrunch doesn't do that for you. But we've got our hypotheses. we've got our p-value is 0.0419. This gives us the test statistic for the ANOVA is the F. It's a ratio of the between group variability and the within group variability. But you don't need to worry about that really, just worry about the p-value here. So the p-value is 0.0419. If we're using 0.05 as alpha, that means we'll reject H0 and say that there is sufficient evidence to conclude that at least one of these means differs from the others. All right. So every analysis of variance comes with an ANOVA table that's got some different things on it. It's got, among other things, it's got the p-value, the test statistic, and then these things we'll talk about. We'll come back to in just a minute. So these tests, ANOVA doesn't tell us what direction, if there's a difference, what direction the difference is. So it can't tell us, right off the bat that one of these is different. Well, it tells us that at least one of them is different, but it doesn't tell us which one, and it doesn't tell us which direction it goes. To determine that, there's a few things you could do. You could run some tests after the fact called post hoc tests. You could also, though, what we're going to do, just to keep it simple, is we're just going to look at what these means are. So it looks like here, after the experiment is over, the diet group had a mean of 246.4, the drug group had a group of 256.4, and the diet and drug group had a mean of 208. So it looks like the diet and the drug, not surprisingly, is the most effective treatment by far. It looks like the diet and the drug are not too far apart, but the diet and drug together a good bit less than the other ones. Let's do another example. If we look at textbook prices by discipline, we've got textbook prices from a bookstore from 4 different disciplines. So go back to StatCrunch, run one-way ANOVA again, stat ANOVA one way. This time we're going to select these 4 columns. Click compute. It gives us the mean prices and the ANOVA table. So this time there are 4 groups. So our null hypothesis is mu1 equals mu2 equals mu3 equals mu4. And then the alternative is still that at least one of the means is different from the others. Our p-value here is 0.8329. And if we're using 0.1 for alpha, that means we would fail to reject H0 and say that there's not sufficient evidence to conclude that any of the means differ from the others. Okay, so that's how to run the tests. Let's talk about the effect size. To talk about effect size, we need to go back and look at 2 of the quantities from the ANOVA table. We talked earlier in the course about the sum of squares as part of the process of computing the standard deviation. Well, sum of squares is a measure of variability for 2 different things. We've got the error is the within groups, and the columns is the factors. So you might see that written as the sum of squares between groups, columns, or sum of squares for the factor. Those all mean the same thing. The effect size that we want, in this case, we want to know what is the percent of total variability that can be explained by the factor. So in this case, we've got sum of squares between groups, so sum of squares for the column, divided by the total sum of squares. So this is the amount of variability between the groups divided by the total variability. So how much of the total variability can be explained by the factor. And so we just take the sum of squares between groups, divide it by the sum of the squares total. When we do that, the rough guidelines are small is 0.1, moderate is 0.09, and large is 0.25. So, in this case, we've got sum of squares for the columns. The factor is 2965, divided by the total sum of squares, which is 71,394. That gives us 0.0415. So 4.15% of the variability in textbook price can be explained by the subject of the book, by the discipline. So that's a small effect, according to these guidelines, 0.01, 0.09, and 0.25. Okay, so that's the effect size. So the coefficient of determination, R squared, and effect size for ANOVA are all mean the same thing. All right, so let's talk about how to do this in SPSS now. So if we wanted to compare the mean amount of time people spend studying per week for different family structures. So in this variable, we've got household structure, which is single parent, both parents, or a parent and a step parent. We're going to go to Analyze, Compare Means, one-way ANOVA, and we've got number of hours spent studying per week. That's going to be our dependent list. Household structure is the factor, and I always want to see the descriptive statistics. So under Options, put a check mark by descriptives, and then that'll give you the mean and the standard deviation for each group. So if you click OK, then it gives you our descriptives, the mean and standard deviation for each group and the sample size, and it gives you the ANOVA table. So copy that over, and we've got three different groups. So our null hypothesis is mu1 equals mu2 equals mu3. The alternative hypothesis, as it always is for ANOVA, is that at least one of the means differs from the others. From the output here, we see that the F-test statistic is 5.939, and the p-value is 0.006. If we're using 0.01, I put 0.001 here, but regardless, you would reject H0 and say that there is sufficient evidence to conclude that the mean amount of time differs based on the family's, the structure of the family. To calculate the effect size, we go to the ANOVA table, get the sum of squares between groups, that's 145.268, divided by the total sum of squares, 597.757. And that gives us 0.2430. So 24.3% of the variability in the amount of time a teen spends studying can be explained by the family structure. This is a fairly large effect. It's not huge, but it's fairly large. All right, so that's all there is with that, and let me know if you have any questions.